mini lecture is going to look at the idea of floating and sinking and its relationship to Archimedes Principle, density, and buoyancy. So you probably know that general mantra, how we know if something sinks or something floats. And we typically say, well, if something is more dense than the fluid, it sinks. And if it's less dense than the fluid, it floats. Well, where does that come from? Where does that idea of density in relationship to sinking and floating come from fundamentally? And so we're going to look at that fundamental idea of floating and sinking. All right, so let's imagine that we have an object fully submerged in water. And we place that object fully submerged in water and we let go of it. It can do one of three things. It can stay put, it can sink, or it can float. So let's look at those three ideas and what that would have to tell us about the forces acting on this object. So we said it could stay put, it could float. And what does that mean? That means it's going to rise to the top. If it's an object that would normally float in this fluid, then it would rise to the top. So that's what we mean in this situation. Or it's an object that normally sinks in this fluid, and therefore it would move to the bottom. I'm going to put a comma there. Okay. So it's going to stay put, it's going to rise to the top because it normally would float, or it's going to move to the bottom because it normally sinks. So let's look at what that means in terms of the motion of the object, and if it's changing or not changing its motion. That's really looking at a force analysis. So let's look at what those forces might look like in these three scenarios. We know that there are two interactions happening with this object. We have the force of gravity, and that's between, we're just going to call this a block, and the earth. We know that points in the downward direction. And we also have the buoyant force, and that's between the block and the water, or the fluid. We'll just call it a fluid to be totally generic, because it works for all fluids. And we learned in our discussion of buoyancy and Archimedes Principle that always acts in the upward direction. All right, so here are our two forces. Now, if the object is staying put, we're going to do that. We're going to do a logic model in terms of what then does the free body diagram or the force diagram look like for that block. Well, we know in all three cases the force of gravity is going to be the same. Why? Well, the mass of the block doesn't change whether it stays put, floats, or sinks, and therefore the force of gravity doesn't change. It's just the mass of the object times g. So those three are identical in all three of our free body diagrams analysis. If I let go of the object and it stays put, well, that means that it's not changing its motion. And if it's not changing its motion, the net force, or the acceleration, is zero. Therefore, the net force is zero. Therefore, the downward forces and the upward forces have to cancel each other out. And so our buoyant force must be equal to our force of gravity. Again, it's staying put. All right? Now, what if it floats? Well, if it rises to the top, that means that it's changing its motion in the upward direction, because it was stationary when I let go of it. It was stationary right at the very beginning, and it started to move upward. Therefore, the velocity is upward. It's increasing in velocity. It's changing its motion in the upward direction. The net force must be positive, so the ups must be beating the downs. And therefore, our buoyant force must be larger than our force of gravity. And in the case of the object sinking, well, when I let go of it, it's at zero velocity, and it starts to move in the downward direction. Well, the velocity is in the downward direction. It's speeding up. It's going from not moving to moving. Therefore, the acceleration must be in the downward direction. Therefore, the net force must be in the downward direction, and our downward forces must be bigger than our upward forces. So in this case, the buoyant force must be smaller than the force of gravity. So this is how the buoyant force would look given the object doing one of these three things. Now, it can't do all of these three things. It can only do one of them. All right. So if this is the case, how then does this get to our mantra of the density idea? Well, we have to remember a couple of things. We have to remember Archimedes' principle. Archimedes' principle told us that the weight of the displaced fluid is equal to the buoyant force. So, remember, B is the weight of the displaced fluid. Now, that's the case in all three cases. B is the weight of the displaced fluid. Okay, so if, in my case of staying put, that tells me that the weight of the displaced fluid is equal to the force of gravity. Well, the force of gravity is the weight of the object. So this tells me that the weight of the displaced fluid is equal to the weight of the object. Now, if we consider both of those objects from a volumetric standpoint, now, the weight of the displaced fluid is the amount of fluid that was displaced. The volume of fluid that was displaced is what I took the weight of. The object has the volume of that displaced fluid because it took up the space. So in this case, the volume of the block is equal to the volume of the displaced fluid. Now we're going to find that's the case in all three, right? Because the block is taking up the space of the fluid that it's displacing. All right, so here we have a situation, in case one, we have a situation that the force of gravity is equal to the buoyant force. The weight of the displaced fluid is equal to the weight of the object. And of course, the volume of the displaced fluid is equal to the volume of the object. Well, we know that the weight is mass of the fluid times gravity is going to equal the mass of the object times gravity. Okay? Well, if that's the case, then we know that the mass of the fluid has to equal the mass of the object. If the mass of the fluid is equal to the mass of the object, and they're occupying the same volume, then the mass of the fluid over the volume has to equal the mass of the object over that same volume. Well, this is the density of the fluid has to equal the density of the object. All right, so there's our first scenario. If I put an object in water and it does not move, we call that neutral density, right? That tells us that the density of the fluid and the density of the object are the same. And therefore it doesn't sink or float. It stays wherever I put it. And what if I put it deeper? Well, the force of gravity hasn't changed, the buoyant force hasn't changed, so it's going to stay deeper. It's going to stay put wherever I put it. And perhaps you've witnessed this. If you've ever had a helium balloon, of course we know the helium balloon rises up, right? But at one point, we can look at this example later, at one point when the helium starts to disperse from that balloon, leak out of that balloon, it starts to get smaller. Volume might be important there. That the balloon kind of stays suspended in the middle of the room. That's sort of a fun little phenomenon. Little kids love it. If you take that balloon and you put it lower to the ground, it stays put there. If you take that balloon and put it up high, it stays put there. Anywhere within the fluid of the room, air is a fluid, anywhere within the fluid of the room, that balloon just stays put. Its density at this point is equal to the density of the air. All right. So let's look at the case of an object that floats. Now we said, let's resell this. We said for an object that floats, that I put within the water, the buoyant force has to be greater than the force of gravity. All right? Buoyant force is going to be greater than the force of gravity. This is for a fully submerged object. That is key, a fully submerged object. Well, that tells you that the mass of the displaced fluid is times g is greater than the mass of the object times g. Getting rid of the g, we find that the mass of the displaced fluid is greater than the mass of the object. All right, well, they're both covering the same volume, okay? So again, this is a fully submerged object. And when I put that fully submerged object in the water, it displaces the volume of water equal to its own volume. So, similar to the last derivation, that means that the mass of the displaced fluid per volume is greater than the mass of the object per that same volume, normalizing them. And therefore, the density of the displaced fluid is greater than the density of the object. And so that leads us to knowing when something floats, right? The density of the object is less than the density of the fluid. The density of the fluid is greater than the density of the object. Now that causes an object to float, to rise to the top of a fully submerged object. But what happens when it gets to the top? Does it keep going? What changes? It stops at the top. So I'm going to pause for a moment. In our analysis here of an object that sinks, you probably can see where that one's going. And I just want to talk a little bit about a floating object for just a second. When an object is floating, so not the scenario I've presented here, not when I've put the object into the water and released it and it rose to the top, but when it's actually floating. Let's just draw a picture of that. When an object is floating, part of it's above the water. Take any object that's floating and you will see that part of it is above the water. What happens to my force analysis? I still have the same two forces acting, okay? Has the force of gravity changed? No, it's the same object, same mass. So the force of gravity is the same. What about the buoyant force? All right, well, we can think of it in two ways. We can analyze it and say, has it changed? Well, we know that the buoyant force is the weight of the displaced fluid. Well, since less of my object is submerged, then less volume of that object is taking up water space because some of the volume is outside of the water. And so less water is displaced, and therefore it has less weight, and the buoyant force must go down. And indeed it does. Another way we can think about it is, well, now I only have the forces on the bottom, no forces on the top, and I'm higher up in the water, so those forces are less, the pressure is less, so those forces are less, and therefore the buoyant force must have gone down. So both of those reasons tell us the buoyant force has gone down. So once the object is risen to the top and floating, we know the buoyant force goes down. But what is it? Well, if the object is floating, it's not moving. If the object is not moving, then it's not changing its motion. If it's not changing its motion, the net force is 0, and therefore the ups and downs have to match. So, when floating, the buoyant force is equal to the force of gravity. It's not a very good equal arrow, is it? There. It's a very squeaky marker. So let me reiterate that. When floating, the buoyant force has to be equal to the force of gravity when floating. All right? So if I push that down, if I push that object down, I am increasing the amount of displaced fluid. I am increasing, therefore, the buoyant force. It's now greater than the force of gravity, and if I let go of it, the buoyant force is larger until enough of that object is above the water, thereby decreasing the buoyant force to the point where it's equal to the force of gravity and no further change in motion would happen. So, an object that floats, we've already deduced that that means that the density is less than that of the surrounding fluid. For an object that floats, if fully submerged, the buoyant force is going to be greater than the force of gravity. But once floating, that buoyant force must be equal to the force of gravity. And less of the object is submerged, so less of the water is displaced, and that makes sense that the buoyant force has now gone down to the point where it's equal to the force of gravity. So imagine, just to play it out one more time, you're in a boat. You're in a boat and the boat's floating. And the amount of volume displaced, the weight of that fluid must be equal to the force of gravity of the boat. Now you start loading things into the boat. So I put something in the boat. Well, now the force of gravity of the boat has increased, so that arrow gets bigger. And for that instant I put something into the boat, the force of gravity is greater than the buoyant force. So the object starts to move down, the boat starts to sink until enough water is displaced that the buoyant force has now once again equaled the force of gravity. I put more stuff in. Well, now the force of gravity went up. As soon as I put that stuff in, the force of gravity is larger than the buoyant force, and the object starts to sink until the point at which the buoyant force is equal to the force of gravity, and then the object will float. Now, when you step into the boat or when you add weight to it, you do notice that it goes down and then sort of rises back up and kind of gets to a settling point. That's because as soon as those forces are equal, motion doesn't stop. Motion goes at a steady rate until the buoyant force then becomes bigger, and the motion has to reverse itself until that equilibrium is achieved. So you can analyze that on a much larger detail. I don't want you to lose the sense that once those forces are equal, motion stops. That's not correct, of course. But you can think about how the motion doesn't stop, therefore the buoyant force continues to increase until it's larger than gravity, and then that is going to balance itself out eventually. And so work through that on your own, but keep in mind this idea of an object that floats. All right, so what about an object that sinks? Well, that's our last scenario, and I'm going to guess that you're going to be able to do that analysis relatively easily based on this idea that we've developed. All right, so in this case, the buoyant force is less than the force of gravity. Well, the fully submerged object, of course, that means that the mass of the displaced fluid times g is less than the mass of the object times g. Our g's go away. Therefore, the mass of the displaced fluid is less than the mass of the object. Those are occupying the same volume, and so the mass of the displaced fluid over that same volume as the mass of the object tells us that the density of the fluid is less than the density of the object. And we know that if the density of the object is more dense than the fluid, it's going to sink. Now, what happens if I let go and it sinks? Does it ever stop? Well, a fully submerged object doesn't change its buoyant force, so the buoyant force is never going to change. And if the object doesn't change its mass, the force of gravity is never going to change. It's just going to sink and sink and sink and sink, and it's never going to stop until it hits the bottom. And once it hits the bottom, I have a new force added, that normal force of whatever the bottom is. And then that normal force will be as big as it needs to be to balance the downward force of gravity. So, once an object starts sinking, it is going to keep sinking unless you make a change. So let's imagine then how we might make a change to an object. Well, we could throw something over the boat, right? We could lose some mass, therefore decreasing the force of gravity, hopefully to the point where that force of gravity is either equal to the buoyant force if I'm not fully submerged, or becomes less than the buoyant force and the object rises to the top. Well, how does a fish swim at different depths, or a submarine move at different depths? Well, in the case of a submarine, we have a fully submerged object. Its volume is fixed. And since its volume is fixed, how does it go deeper? If it's fully submerged, happy at a certain depth, how's it going to move deeper? The buoyant force hasn't changed. The force of gravity hasn't changed. Well, it takes on water. It increases the force of gravity. If it increases the force of gravity, it takes in water into its ballasts, takes in that water. Force of gravity goes up. Now it's greater than the buoyant force, so the submarine starts to sink. But if it keeps that water in there, what's going to happen? Well, it's just going to keep sinking and sinking and sinking. And we don't want to do that, right? We don't want to go too deep. We want to get to a point where we're just at a new depth. So what does the submarine have to do at that point when it reaches the depth it wants? Well, it needs to let that water out, decreasing the force of gravity so that those two forces become equal once again. Now, again, it has to do it in such a way that, it doesn't expunge the exact same amount at the depth it wants, and all motion stops. That wouldn't happen. Those forces would be equal, and the object would continue to sink. So it expunges that water a little. It expunges it earlier, and therefore it starts to, and a little bit more, and it does that balancing act that we talked about in terms of going up. So you imagine if something is released and it floats to the top, it kind of bounces a little bit until it equilibrates. The same can be said for a submarine taking on water or letting out water. Fish do the same thing. They make their change volumeistically, if that's a word, by volume. So if they poof out their bellies, they've now increased their volume once in the water. Well, what's that going to do? Is it going to increase the buoyant force or decrease the buoyant force if I increase the volume? I'm going to increase the buoyant force. Right, so remember that's the weight of the displaced fluid. If I make myself bigger, then I displace more fluid, I increase the buoyant force. So I increase that buoyant force, that fish will rise to the top. If that fish releases the air, compresses the air sacs, then they sink to the bottom. All right, so you can change the force of gravity to move within a fluid, or you can change the volume to move within a fluid. Okay, a lot of information about sinking and floating, relating Archimedes' principle to density. All that comes together to describe sinking and floating. It gets us to that mantra of more dense, less dense, in terms of something that sinks or floats in a more fundamental way. Okay, good job.